So as we begin our Module 8, we're going to be taking a look at Chapter 6. We're looking at shear stresses in beams and thin-walled members. So in the previous chapters and previous modules, we've taken a look at some of the normal stress that's due to bending moment for the design of beams. So now what we're going to continue on and do is now also consider shearing stresses due to transverse stress. In particular, we'll look at the design of short and stubby beams. We're also going to take a look at some longitudinal shear and analyze the effects of transverse loading. So within this module, what we're going to do is we're going to take a look and demonstrate how transverse loads on beams generate shearing stresses. We're going to determine the stress and shear flow on horizontal section in beams. We're going to determine the shearing stress in thin-walled beams. We're also going to describe the plastic deformations that are due to shear, and then recognize cases of symmetric and unsymmetric loading. And last, we're going to use shear flow to determine the location of the shear center in unsymmetric beams. So relating back to your textbook, again, this is Chapter 6 that we're beginning here. Two different reading assignments for the first module section, which is 8.1. We're looking at Chapter 6, Sections 1 and 2. And for Module 8.2, we're going to be looking at Chapter 6, Sections 3 through 6. So as we get into Chapter 6, again, we're going to break this into two different sections, Module 8.1 and Module 8.2. In Module 8.1, we're going to go over the introduction, take a look at the shear on horizontal face of a beam element, go through a couple concept applications, look at shear stressing in a beam, talk about shear stressing in common beam types, and then a little bit further discussion on the distributions of stresses, and then do another example problem. Then when we get to Module 8.2, we're going to look at longitudinal shear, go over a couple concept applications, look at shearing stresses in thin-walled members, plastic deformations, another example problem utilizing some of that theory and equations, and then look at unsymmetric loading of thin-walled members and shear center, and do a couple more applications and problem solving. So now we'll begin Module 8.1. So in Module 8.1, what we're going to do is we're going to take a look at the shear on a horizontal face of a beam element, look at shearing stresses in a beam, shearing stresses in common beam types, and then talk about the distribution of stresses in narrow rectangular beams in particular. So within this module, we'll go through some of this theory, talking about those concepts above, look at some of the governing equations, talk about some practical applications, and do some problem solving together. So as we do an introduction to shearing stresses in beams right here, we're going to take a look at here is the transverse loading applied to a beam. Now this is going to result in normal and shearing stresses in the transverse sections of the beam right there. So if we come over here to the left to our diagram over here, we can see we have on the left-hand side over here, we can show all of our stresses on the elements in the area right there. So you can see here we have our transverse section right there. We can see our shear stresses, and we can see our normal stress right there and our shear stress right there. So we have our tau xy dA as a shear stress there. We have our tau xz dA, and we have our sigma x dA. So we have our normal and our shearing stresses represented in that. Now, all of these stresses over here on the left-hand side are going to sum together to give us the resultant shear force and bending moment M. So our shear force V and our bending moment M right over here, which we see in our right diagram over here. So here is our shear force right there. There's our shear force V right there. And there is our bending moment right here, M right there. So we can use this relationship right here that all of these stress elements added together are going to be equal to the resultant shear and bending moments over here that we see in this diagram. So what this is saying now then, by that relationship, that knowing that we can sum all the individual stresses up to be the resultant shear and bending moments, that we can use the distribution of the normal and shearing stresses to satisfy the following relationships. So just as we've done before when we're looking at our equilibrium equations here, we want to break things down in terms of their components. So if we go back to our diagram on the left, we can notice that this is in 3 dimensions, x, y, and z. So we want to look at each one of those components separately. So let's just start with x first. We can say the summation of the forces in the x direction is equal to the integral of our sigma x dA, which is equal to 0. So our sigma x dA, that is our normal stress right there, and our x direction right there. And if we go over here in our x direction, that's the only thing acting here. So that is our stress in our normal direction right there. And then we can, at the same time, in the x direction, take a look at our moments in the x direction. So what moments do we have acting in the x direction right there? Well, that's the summation of all these individual ones right here. So that's what our integral is right there, the summation of all of these right here. So we have now our y times our shear stress in the xz direction. So let's take a look. Here's our shear in the xz direction right here. So right there, so this is going to be our moments about our x-axis right there. So that is going to be times this perpendicular distance right there. Now what else is going to create a moment about that x-axis right there? Well, we're going to have our shear xy right here times now our z direction right here. So we're going to have this z direction right here. So we have this distance right here. So we have those two distances right there. So it's force times a particular distance. So if we're going about that x-axis right here, then it is going to be our z and our y are going to be our two perpendicular distances, and make sure we have the corresponding right shear stress that creates that moment about our x-axis right there. Now we can do the same thing for the forces and moments, force in the y direction, moments about y, force in the z direction, moments about z, and these relate back to our textbook to equations 6.1 and 6.2. So now we can come over here and say, okay, what are the forces in our y direction right there? Well, we just have our tau dA, tau xy dA right there, so our tau xy dA right there for our force right there, which is going to be equal to our negative v right here. Now, why is it equal to negative v? Well, we come over here to our free body diagram over here. In our y direction, we do have a negative v acting right there. We didn't have that in our x direction. If we go back up here and look at our x direction, there is no forces acting in our x direction. So the only force right here is this negative v right there. So now we can say those are equal to each other. Then we can do the same thing in our z direction right here. So the forces in our z direction, we go over here to the free body diagram. Well, there are no forces right there. But in our z direction over here, we do have this relationship right here, which is our tau xy dA. So that's going to be equal to 0 for our z direction there. Now, similarly, we can go back up to our moments again now. So let's take a look at our summation of moments in our y direction right here. So we'll clear this off just for a second so we can see again. And in our y direction right here, we can see in our moments about our y direction right here, we have our z right there times our sigma x right there. So there's our sigma x right there, dA, times our distance in our z direction right there. And that's going to give it about this y-axis right there. So our force times our perpendicular distance right there. Then we're also going to have down here, if we do our summation of moments about our z-axis, if we clear this guy out here, about our z-axis down here. So now we can say, well, what's acting about our z-axis? If this is our z-axis right here, what's going to create a moment about right there? Well, we have now our sigma x right here, again right there, times now our negative y direction as we go down right there. So there's our force times our perpendicular distance right there. So we can see, okay, that's going to create a moment about our z-axis right there. And this is equal to m because we can see there is a moment over here as well. So that's where we get that relationship there. So again, please reference back to equations 6.1 and 6.2 in your textbook. And we can clearly see this is the same as we've done before for any free body diagram, looking at all of our forces, summation of forces in the x, y, z, summation of moments about x, summation of moments about y, summation of moments about z right there. And that's where we get these relationships from. And again, please relate this back to equations 6.1 and 6.2 in your textbook. So one thing to note here, let's zoom in a little bit right here on this stress element right here from a section of the transversely loaded beam. So we can see that there. And one thing that we want to note about this here is that when shearing stresses are exerted on the vertical faces right here, so you can see there's the vertical face right there, and the shearing stresses right there. Equal stresses must be exerted along the horizontal faces. So we can now see, well, there's one there, then the vertical, there we go on our horizontal right there. So the same thing right here. We can see on the dotted line there, vertical and our horizontal right there. The other thing we know is that longitudinal shearing stresses must exist in any member that is subjected to this transverse loading. So if we have a transverse loading, then we're going to have these longitudinal shearing stresses. They must exist. So now let's take a little bit more in-depth look at the shear on the horizontal face of a beam element right here. So we're going to consider this prismatic beam AB. So we can come over here to the left in our diagram over here, and we can see we have this beam right here. So we can see this is a simply supported beam at A and at B right there. We can see our two support types right there. We can also see in this diagram right here that we have this load P1, P2, and a distributed load W right there. And we have some distance out here, X, where we can get to this section C right there. And we can see if we section this right here, here's what the cross section of this looks like right here in our YZ direction. So this is a transversely loaded beam with a vertical plane symmetric cross section. So there's our cross section right there. We can see it's symmetric across that vertical plane right there, but not symmetric across our horizontal plane there. So now the next thing we want to do is take a look at an individual element on this beam right here. So if we come down to this next diagram right here, we can see we have a short section of the beam with a stress element that we've defined as our CD, D prime, C prime. So if we look in right here, there's our C, D, D prime, C prime. And then this again right here is going in our X direction right there. And this over here is our Y, Z plane right here with our X coming out of the board at us right there. So what we're looking at here is this individual square element right here if we're looking at it from this plane, but if we're looking at it from the YZ plane, it just has the same shape that we see up here we showed in our initial diagram as well. So now what we want to do is let's zoom in on that individual element right there. So you can see between C and D, that's our delta X right there. And if we talk about this here, we come down and draw this out down here, and we take a look at our exerted forces on that right there. So if we take a look at the top right there, we showed that delta X right there, what forces are occurring on that? So we're doing out our free body diagram on that element right now. And we say, well, we can go back up to our initial diagram up here, and we can see this distributed load. So, side note right now, this is why it's very good practice to have all these different diagrams drawn out. And I know on this slide right here, I've kind of piled them all on top of each other on one slide just so we can look at them at the same time. But if you're working on a homework problem or an exam problem, this is something where you have one of these per page would be great, or even two per page, as long as it's big enough that you can actually see what's going on. Then you can flip back to the previous page where you had the initial diagram and look at it and double check everything, and then do exactly what we're doing right now and say, okay, what are the forces acting on this element as I'm drawing out my free body diagram in the bottom here? Well, if I go back up here, as I was saying, we can see at this section C right here, where we're looking at this element right there, we can see this distributed load W. So that's where this W down here in our free body diagram comes from, is from that distributed load that we're seeing in our initial diagram up top. So now, what other forces are acting on this element right here for a free body diagram? Well, we have our shear forces right here on either side. So we can see right here, we have our V prime D and our V prime C acting right here on C and D sides of this element right there. And the next thing that we note right here is this delta H. It's moving along in our X direction right here. Well, what is our delta H? Let's come up here for a second right here. And our delta H is this horizontal shearing force that's exerted on the lower face of the element. So that's exactly what we have right here. That's the lower face of the element. So this right here is our horizontal shearing force, our delta H. And again, note this is acting in the X direction. So this is why this coordinate system becomes very important for us right here. So we can see this is our X direction. Then we go back up top to our element right here. Well, if we're looking at the side view of that element right there, that is our YZ plane. We can do our right hand rule, double check that everything's positive, it should be positive, and pay attention to our sign convention right there. Pay attention and always label out your axes somewhere on each page so you know what direction you're talking about. And that becomes important right here. Again, we're talking about this delta H, and it's the horizontal shearing force. Well, what direction is the horizontal direction going in? So in our case here, we can clearly see that that is moving in our X direction. So now leads us to the question of how do we define our delta H. So our delta H, we can go back to equation 6.3 in our textbook right here, and we have this governing equation here, that our delta H is the moment about D minus the moment about C, all over our moment of inertia here, our I value right there, times the integral over our area of Y dA. So now we want to come back over here and take a look at everything and make sure we understand what all those are. So our moments about D, that's D right there. There's our moments about C right over here at this point right there. And we can say now this is all over I. We can look up I for this shape from the appendices right there to get our value for that there. And we say the integral over the area right there. Well, we can figure out our cross-sectional area for our element right there of Y dA. And we can see, okay, this is our Y direction right there as we're moving up right there. So that's our Y dA right there. So now we understand, at least visually, from our diagrams and our elements right here, of what each of those variables are that are going in to calculate this delta H on the bottom there, which again is that horizontal shearing force that's exerted on that lower face of the element. This is a lower face there, and this is a lower face right there as we're looking at this in two different views. So now what we want to do is, now that we have our free body diagram here, we defined what H is right here, let's take a look and look at our summation of forces right here, do our equilibrium analysis for our X direction right there. So what forces are acting in our X direction right here? Well, summation of force in the X direction, we can come back down to our diagram here and look at this, and we can say, well, I see three different forces that are acting in my X direction right here. So I can see I have my delta H right there. I've also got my sigma C dA and my sigma D dA right there, which are my stresses times that distance right there, the horizontal, sorry, times that differential area right there. So you have the stress at C times the differential area, and then the stress at D times the differential area right there to give those two forces as well. So we can come back up to summation of forces in our X direction. Well, it's an equilibrium, so it's 0, so it's equal to our delta H right there that we're seeing right here. Now plus the integral of all these differential areas times the stresses at those right there for each of those elements right there. So we're going to sum those all up with the integral right there. So that's our sigma D minus our sigma C times our dA, the differential element right there. So now looking at that equation we see here, 6.3 for our delta H right there, one thing that we want to note here is we have this value Q, which Q represents the first moment with respect to the neutral axis right there, and this is given by the relationship for the integral over the area of y dA. We notice that that goes right there from equation 6.3, so that's our Q value right there. Now we can also make a note that if we're saying the moment at D minus the moment at C, that's going to be the change in moment with respect to the position X right there, because if we look back to C and D right there, that's moving along our x-axis right there. So this is just the change in moment with respect to that position along the x-axis right there. So that's our dm dx delta x right there. There's our times our delta x right there. Where again, this is our delta x right there is the difference between C and D right there. So we can take a look at this, and this is going to be equal to our v delta x right there, because dm over dx will be our v value right there. So now we have this md minus mc that we can replace now by this v delta x. So we have these two relationships. We can replace this integral with q and replace this md minus mc with a v delta x right there. So we can sub these in, and this is where we get our equation 6.4 in our textbook right there, where we have our delta h is now equal to v times q when we replace the top of this and this right here with our v right there and our q right there, times our delta x at the end of this right there from our delta x right there, and this right here is over I right there. So this is our equation 6.4 from our textbook, and we can rearrange that a little bit. And if we want to find our shear flow or our lowercase q right there, this goes with equation 6.5 in our textbook right here, where lowercase q is equal to our delta h over our delta x. Well, now we have an expression for delta h right there, where our delta x's will cancel right there. So we're just left with q is equal to v times capital Q, which again is that first moment with respect to our neutral axis right there, all over our I there. So this again goes back from equations 6.3, 6.4, and 6.5 in our textbook right there. So if you want a little bit more information on the derivation of these, please reference that section within your textbook. So now we've derived an expression for our shear flow, and this again relates back to equation 6.5 in our textbook. We have our shear flow, our lowercase q, was equal to this delta h over delta x, so we showed we had a relationship for delta h that we could plug in there. We cancel all our delta x right there, and we were left with our v q over I right there, which is again our shear flow right there. So where we have an expression now for q and for I, we have a relationship here, so where our q is equal to, and we've shown this before right there, the integral over the area of y dA right there. So if we go back over to our diagram right here, this is our y direction right there. So it's the integral of our area right there of y dA. And then this is our first moment above this y1 in our particular case here. So there's our y1 for this case right there. Now our I value is equal to the integral over a plus a prime of our y squared dA. Now our I right here is the centroidal moment of inertia of the entire cross-sectional area right there. So this is the second moment of the full cross-section. Now the thing to note, this was all above our neutral axis. So this is our neutral axis. If I draw a line straight through here, this was our neutral axis right there. Now what if we want to deal with down here where we have our C double prime, D double prime area right there? Well, we can do the same type of result right down here for the lower area that we're interested in there, below our neutral axis right there. Where now instead of our 6.5, we can rearrange this, and this is now going to be lowercase q prime is equal to our delta h prime all over delta x right there, which then goes into a v. We can see our shear force v right there times our q, capital Q prime right there, over our I, which is going to be equal to a negative q prime right there. So we can say is q plus our q prime is equal to 0 right there if we look at the relationship between those variables right there, which is this is going to be our first moment with respect to the neutral axis again still right there, where this is the neutral axis right there, which also lets us know if we go back into this relationship right here for our delta h on the top there, that our delta h prime is equal to negative delta h right there. So q plus q prime is equal to 0, and now we have the relationship of delta h prime is equal to negative delta h right there. So now let's take some of those governing equations and that theory that we just looked at there and apply them to an actual example problem here. So the problem we're going to take a look at now is concept application 6.11, and you can reference back to your textbook for this problem as well. But I want to go through this with you. So what we have here is we have a problem statement and initial given diagram for this problem right here. Now the thing we can note is they've only given us one view. So just like we went through earlier in the module, sometimes we might need to look at this in two different views, in two different planes to kind of get an idea of exactly what's going on. So So in this problem statement, they tell us that a beam is made of 3 planks. So we can come down to our diagram. There's our 3 planks. We got our top plank, our bottom plank, and our center vertical plank right there. And they also tell us now that each of these has dimensions and a cross-sectional area that we can reference from those dimensions, and it is 20 millimeters by 100 millimeters. So this is something we want to pay attention to right here. This is given to us in millimeters, and we can see down here they're giving us forces in newtons, which is in terms of meters. So this is something that we may want to convert right away on our setup page to meters rather than millimeters, just so we can plug in and not mess up our dimensions. And we do our dimension analysis out, we really do want to double check that and make sure everything is in the correct dimensions. So from this right here, we can see this is for our cross sections. We can multiply those to our cross-sectional area. Now they tell us that these are nailed together. So we can take a look at, there's a nail right there, and there's a nail right there. Now this is what we're looking at the other direction right here. They tell us that the spacing between the nails is going to be 25 millimeters, which again, we want to convert to meters. So that's going along the other length of this right here. They also tell us that the vertical shear in the beam is given to us as V is equal to 500 newtons. So again, newtons is in terms of meters right there. So that's why these other ones we may want to convert to meters right away. Now, what are they asking us to solve for in this problem? Well, they're asking us to determine the shearing force in each nail. So that's what we want to look for, is the shearing force in each of these nails. So now that we've had a chance to read through that initial problem statement, look at the given diagram, our next step if we were solving this out by hand would be to create our setup page. And recall on our setup page, what we're going to have there is our given information, what they're asking us to solve for, any assumptions that we're going to make. So within the given information, what we want to do is read through that problem statement, look at the initial given diagram, and determine, okay, what do we have? What do we know? And within that there, we want to have 4 different things for each of those. We want to have the variable name, we want to have the numerical value, we want to have the units, and if we're converting from millimeters to meters or between units, have that there as well. And then we want to have how it relates back to our problem there. Then below that, we have our find section. We write out everything that's asked us to solve for in the problem right there. And below that, we're going to have any assumptions we're making for our solution. Now, with that information from that setup page, then what we can do is come up with a procedure for analysis. So that's what we're going to do here, is come up with a procedure for analysis. So we can see we've copied over our initial given diagram right here. We can see all of our dimensions right there. We have this top plank, the length of 100 millimeters. We have the width of our middle plank of 20 millimeters. The distance between the top and the bottom is 100 millimeters there. And the top and bottom thickness of these planks right here is 20 millimeters as well. So this is a composite beam made of 3 boards nailed together. So we write that out right here. We have a beam that is made of 3 planks that are all nailed together right there. Now we know the spacing between these nails from the problem statement. This is given to us as at 25 millimeters, and we know that the vertical shear in the beam is given to us as V is equal to 500 newtons. So again, these are all things that we're going to want to include in that setup section under our givens for this problem right here. And under our find section, this is what we have right here. We want to determine that shear force in each nail. So right here, these 2 nails, we want to find the shear force in each of those right there. So now as we have this information, we read through it, our next step is to come up with that procedure for analysis. So for our solution, if we're thinking about this here, what we want to do is first we're going to want to determine that horizontal force per unit length, or our shear flow, which is that value Q right there, on the lower surface of our upper plank. So we're just going to look at just the upper plank right here first right there, and just the lower surface of that right there to find that shear flow. Now this should be setting off some red flags. We've seen some good equations earlier in this module right here that we can reference back to for our shear flow for this portion of the problem right there. Then from there, once we have that information and determine the horizontal force per unit length right there with that shear flow, next we want to calculate the corresponding shear force, so we can relate that with another one of those equations we saw earlier in each nail. So now we have this procedure for analysis, we can use this as we start going through and beginning our solution and choosing our governing equations. So as we step through that procedure for analysis and begin our solution right here, one of the first things we want to do is draw out a modified version of our diagram right here. So we can see in part B right here of our diagram from our initial given diagram, we can see we have this top part right here highlighted, our A section right here. Because again, we recall that we wanted to look at this for just the upper plank right there. So if we're determining that horizontal force per unit length, or our shear flow right there, our Q, for the lower surface of the upper plank. So we want to just look at this upper plank right here. So I have all my information drawn into this diagram now. We have our neutral axis. We've divided this right in half right there. So we can see there's our neutral axis right there. Now why is this 0.06 meters? Well, because if we looked at this whole distance between the bottom surface and the bottom surface of these two guys, or I guess the top surface of this bottom one and the bottom surface of this top one right here, was what would be a 0.1 meters right there, where each of these were a 0.02 right there. So half of 0.1 would be 0.05 plus half of 0.02 would be 0.01. We add those together, and that's why this distance from our neutral axis up to the bottom surface of this upper plank right there, our y bar, is equal to 0.06 meters. So you notice I've converted to meters from millimeters now, so everything's going to be in terms of meters and make that easy for us right there. So again, that's taking half of this distance right here and half of this distance right here, which is the thickness right there, and adding that together to get that distance from our neutral axis back up to our point C right there in this upper plank right there. So now the next step in this here, if we know that we want to find this shear flow right there, our Q value, we can go back in our module, back in this lecture here, take a look, and we can see, okay, earlier we showed a definition. We showed a governing equation for our shear flow, our Q value right there, which was our shear force times this value of Q right here, all divided by I down here. Now, our V was given to us in the problem statement right here. So if I erase that there, this was our V value that was given to us of 500 newtons right there in the problem statement. So that we have right there, but now the question is, where do we come up with this Q and where do we come up with this I? Well, we do have some governing equations that we can utilize that we can see down here for our Q and our I value right here. So our Q is relatively straightforward. We have this cross-sectional area times our Y bar. So again, this is why it's great that we have these diagrams and everything labeled right there. We've already gone through where we came up with this Y bar right here. Again, this Y bar was half of this plus half of this right here to get that distance from our neutral axis up to the center right there where our C prime is right there. So we can do that right there, and this is our 0.06 meters right there. So this is where our Y bar is for this portion of the equation. So now, what we can do, let's clear this off for a second, and we can see we need to find our cross-sectional area next. So we can find this based upon the dimension that they gave us in the problem statement right there. So they told us that we had these dimensions of 0.02 meters and 1 meter right there for this right here, so we can get that cross-sectional area. So there's our 0.02 and there's our 0.1 meter right there. So we can multiply those together right there, and that'll give us our cross-sectional area. So our Q is equal to that cross-sectional area, which again is this times this right here, times now our Y bar, or this value right there. So this gives us our capital Q value right there. So we can multiply that all together, and we double check meters times meters times meters will give us meters cubed right there, which is what we'd expect for units for our Q right there. So we have for Q value 120 times 10 to the negative 6 meters cubed. And that's where we can come back up over here to this governing equation up here for our shear flow. And we can plug in now for our Q value right there, 120 times 10 to the negative 6 meters cubed. Now as we move on down below here and we want to calculate our I value right here, well, we recall that this is going to be 3 planks. So each of these planks have similar dimensions right here, and we can see that the top and the bottom plank right here are identical. They're both going to be this value of 0.1 meters wide, and we can see our thickness of 0.02 meters right there. So there's 2 of those right there, but we also have in here the center plank right here as well. So those are things we're going to need to consider as we're doing out our moment of inertia here, our I value. So as we're considering those individual sections of the beam again, the top section, the bottom plank right there, and the middle plank right there, we can come up with our governing equation for our moment of inertia for that right there, where I is equal to 1/12 base times our height cubed right there. So we can do that. Then we also have to remember there's also this component for I right here from our second moment of at the full cross section as well, where we have this y squared dA. So all 4 of those are going to contribute to our moment of inertia right here, our I value right there. So let's start with our planks to begin with first right here. So let's just start with the middle plank right here. So we'll erase all this just for a second right here. We'll start with that middle plank right here. So what are our dimensions of this middle plank? Well, our base right here is going to be our 0.02 meters, and our height is going to be our 0.1. So if we have 1/12 base times our height cubed right there, well, there's our base we plug in as our 0.02 meters, and there's our height right there of 0.1 meters, and that's cubed right there. So that takes into account the middle plank, the vertical plank right there. So now let's clear this again, and let's deal with the top and bottom plank here next. So we can say, well, there's 2 of those that are identical. This is 1/12 our base times our height cubed right there. Well, our base now is going to be 0.1 meters, whereas our height is going to be our 0.02 meters right there. So we have 1/12 times our base times our height right there, cubed right there, times 2, because we have the top and the bottom plank that we're taking into account right there. So that takes into account our 3 planks right there. So the next thing that we need to take into account now is our value for Q right here. So this is where we have in this relationship right here, or not Q, but our integral of y squared dA, which is essentially the same thing that we solved for our Q up top right there. So we look at this, and the only difference is now right here is that this is going to be our y squared term when we come in. So that's where this comes in right here. We have that area. There's our dA right there for our area, times our y value right there, which again, this is our y value right there, which was half of this plus half of this together, the distance from the neutral axis right there, squared. So now we can do out our math and find this I value right here for those 3 planks and this relationship right here, and we get this value here. So now this is what we come up here and plug in right there, and this is where we have this 16.2 times 10 to the negative 6 in units of meters to the 4th. So now we can go through with that given V, our calculated value for Q, our calculated value for I, do out our math, and our shear flow, or our lowercase q right here, is now 3,704 in units of newtons per meter. And double check your units with everything right here and make sure that that does come out correct, because you can see here's your meter cubed, cancel the 4th there, we're left with meters on the bottom. So this is a newtons per meter, which is correct and what we'd expect for our units for our Q right there, because this right here is our force per unit length. So if you think about that, shear flow is force per unit length. There's a force per unit length right there. That does check out. So doing that unit analysis is something is very important to double check, especially with something like this, where even though this initial part of this equation was relatively straightforward, we realized we had to plug another equation in for that and another equation into that, which actually had 4 equations within that. So it becomes complicated quickly, and you really want to pay attention to units and use that as a double check. So now we need to go back to that problem statement, even back to our setup page as well, and double check and make sure we solve for everything they've asked us for. Well, no, we haven't. They wanted us to calculate the corresponding shear force in each nail for this 25 millimeter spacing right there. So all we've found so far is we have this Q, which right here is our shear flow, or our horizontal force per unit length right there. So now if we want to calculate the corresponding shear force in each nail for the nail spacing of 25 millimeters, we can use this relationship shown down here, where if we have our Q, which is force per meters, and then we have this distance, which we convert to meters right here. So 25 millimeters becomes 0.025 meters. So if we were to multiply a distance by this value for Q right here, we could see the meters and the meters will cancel. We're left with just the newton. So that's where we get this force relationship here, is this distance, or a spacing between each nail, times this right here, or horizontal force per unit length, or our shear flow right there, our Q value right there. We get that relationship there. So we can now say that force is equal to the 0.025 meters, the spacing between the nails, times our shear flow right there of 3,704 newtons per meters that we just calculated. Again, meters cancel with meters, we're left with just newtons. So that F right there, or the corresponding shear force in each nail, is going to be 92.6 newtons. So let's take a look at that same beam we were looking at before with our horizontal symmetry. So we're going to continue looking at our shearing stresses in this beam right here. In particular, I want to take a look at our average shearing stresses. So these average shearing stresses on the horizontal face are obtained by dividing our shearing force, that delta H on the element, by our delta A of that face right there. So we've already gone through and calculated this delta H. We've seen our relationship and our equation for our delta H there. We know how to calculate our delta A from the face, the shape of that face of the element right there. So those are the 2 things that we're going to use in order to calculate this average shearing stress. So our average shearing stress, if we look down here, this is our tau average right there. So that's our shearing stress right there. And this is obtained again by that delta H over delta A. So that's the relationship we're looking at right there, again, by using that relationship we just discussed above here with delta H and delta A. So we can go back over on the left over here and take a look in this figure right here. We've seen this figure before. So this is a short segment of the beam with a small stress element right there. So the stress element right here that we're looking at here is a C prime, D prime, D double prime, C double prime. So C prime, D prime, C double prime, and our D double prime right there. So again, now we can take a look at this. Here's our horizontal neutral axis right there. So we can see that neutral axis there. And if we go up to the top right here, where our y1 is, which is right at the top of that element C prime, D prime right there, we can see that this is a distance of y1 off of the neutral axis right there. Now, if we're taking a look from the neutral axis to the top surface, this is where we have our C right there, and the distance between our C prime and D prime, as well as our C double prime and D double prime right here, is what we're showing here is our delta X direction right there. So that's our X direction that's moving around right here. So that's our X direction right there. We can see there's our Y direction, and down here is our Z direction right there. So again, this is the YZ plane where we have our X in the center here coming out of the board. So now what I want to do is take a little bit of time and show how we can go from these different views to a 3D view right here. So we have this planar view right here where we can see that whole rectangle, which I'll come over here in light blue and draw out this rectangle right here. So there's our rectangle right there. And then we have over here, in this view right here, we have our YZ view. So looking at the side view of that right there. So this is our YZ view right there. So if we look at that there for this now, this is going to be this view, what we're looking at down here on the side of this shape, right like that there. And so now what we can do is we can say, well, this rectangle, this blue rectangle right there, is this face right here if we're looking at it in 3D. Like that right there. So now we can see that this face is this face here, and this face is this face right there. So we'll trace that out just so we can clearly show that this face right there, whoops, go back to red with this here. So this face right here is the same as that red face. So we can keep the color combination the same for that. So now we can kind of get a visualization between a 3D and then these two 2D planar views of this right here. And that's where we come up with all these different names. And I'm going to switch over here to a yellow for this right here to point to things. So we can see now we have this C prime right here. So this C prime is equal to this face right here is this right here. So this is our C1 prime. This is our C1 prime right there. This is our D1 prime, our D1 prime right there. Our C1 double prime and our C1 double prime right there. And this is our D1 double prime and our D1 double prime right there. And again, that's going along this surface right here on this guy right there. Now if we want to move over to this back surface over here, which is this guy over here, that's where we now have these other variables here. So for now we're over here, it's the same thing, but now this is our D2 as we go back on this back surface over here. Our D2 double prime, our D1 our D2 prime, our C2 prime, and again down in that back corner that we can't see there would be our C2 double prime. So that's how it relates back to those two views up there. So I just want to go over that a little bit before we get into any of the equations here, just so we can understand what the 1 and 2 and the prime and double prime mean. We're looking at this in both these 2D planar views up top here and this three-dimensional view right there. So now let's continue on looking at this average shearing stress right there. So we can say our average shearing stress, our tau average, is equal to this delta H divided by our delta A, where delta H is that shearing force right there. Now we've seen a relationship for delta H in our shear flow before, and this is a derivation back around equation 6.5 in our textbook right there. We had this relationship right here, that our shear flow is equal to our delta H over X. Now we can rearrange that right there, and if we want to solve this for our delta H, we can say delta H right there is equal to Q. We can multiply this up to the other side times our delta X. So that's what we do right there. We replace our delta H with this relationship here of Q delta X. So now we have that our average shearing stress, our tau average, is equal to Q delta X over our delta A right there. So we can still also say now with this here, again, that we have our delta H over delta A is equal to this relationship right here. So we can say that our delta H right here, now if we plugged in for that there, we have this relationship right here from 6.5, that this is equal to V times Q divided by I times our delta T right there. So we can plug this in right there, VQ times I times our delta X right there. So that is now our H value. So we replaced our H with that right there. And then we have our delta A on the bottom here. Well, what is our delta A? A is the cross-sectional area of that surface right there. Well, what surface are we talking about? We're talking about this top surface right here, because there's our delta H right there that we're dealing with right there. So this is the surface we're talking about right there. So what is our area of a rectangle? Base times height. Well, we have our base here of our delta X, and we have our height here of T. So there is our area right there, T times our delta X. So now we have that relationship there. We've now said that our T average is equal to now this value right here that we had for our delta H times our delta X right there. So there's our whole delta H right there from this relationship shown in 6.5. And this is now our delta A in the denominator right there, which is T delta X right there. We can see we have a delta X and a delta X that are going to cancel out. So that now just leaves us that our tau average right there, our average shearing stress, is V times Q all over IT, which is our equation 6.6 from our textbook. So let's erase all the rest of that. So now this is what we have here. For our average shearing stress, we have, there we go, our average shearing stress, what we have here is this equation right here from 6.6 in our textbook with that V times Q over IT. And this is how we did that derivation using some of this relationships we've seen in the previous slides within this module. So now I want to take a look at our shearing stress at specific locations on our element here. So in particular, let's take a look at our upper and lower surfaces of the beam right there. So we have our tau yx is equal to 0 right there. So there's our tau yx on the upper surface. There's our tau yx on the lower surface of the beam right there. And it also follows that our tau xy on the upper and lower edges. So there's our tau xy and our tau xy on the upper and the lower edges right there are also going to be 0 as well. Now, as long as the width of the beam cross-section remains small in comparison to its depth, this is relative right there, the shearing stress varies only slightly along the line of D1 prime to D2 prime. So that's going along this line of D1 prime to D2 prime. So it's not going to vary much along there as long as we follow this right here and the beam cross-section remains small as compared to its actual depth. So let's continue on looking at shearing stresses, our tau xy, and now let's look at this for some common beam types. So the first beam type we're going to take a look at here is our narrow rectangular beam. So this is a pretty simplistic beam, pretty common right there. So we can see now we have a narrow rectangular beam shown over here in this diagram right there. Now let's take a look at some of the dimensions within this narrow beam right here. So for a rectangular beam, we got a base and a height. So there's our base B right there, and there's our height H right here, the total height of this right here. So we can see if we divide this out, if that's the total height, and this is our neutral axis right here at Z right there, well then we'd have half the height there and half the height there. So we're defining C as half the height for this particular case, which is the distance from the neutral axis to the outer surface, which happens to be the same in both directions right there as we're going in this Y direction right there. So notice we are in the YZ plane. There's our Y axis there, our Z axis there, and our X axis coming out at us. So now let's go back over here and we can take a look at equation 6.9 in our textbook right here, where we have the definition now for our shearing stress, our tau xy for this case right here for a narrow rectangular beam is equal to V times Q, our shearing force times Q over IB right there. So now we can reduce this down a little bit now from this relationship here, and we can see for a narrow rectangular beam right here, we now have 3/2 of times our V over A right there. So there's our shearing force right there and our area right there times now 1 minus our Y squared over our C squared right there. We go back over here. C is that distance from the neutral axis to the outer surface. And we can see our Y value right here goes up to, if this is an area that we're interested in right here, so our area right there, this is a distance from our neutral axis up to the base of that area that we're interested in right there. That's our Y value right there that we're plugging in. So again, this is now our equation 6.9. We have 3/2 VA times 1 minus Y squared over C squared right there. And if we're looking for our max shearing stress right there for a rectangular narrow beam, this is simply just going to reduce down to 3/2 V over A, which relates back to equation 6.10 in our textbook. So let's take a little bit more in-depth look here at how we get from 6.9 to 6.10. When we're looking at this, how do we reduce this equation down to what we see here when we're talking about our max shearing stress right there? Well, we can do that by taking a look at this graph over here. And we can see that our max shearing stress right here, our tau max, is going to occur at this point right here. Well, what is this point right here relating back to our equation? Well, this point right here is when our Y value right here is equal to 0 on that Y-axis right there. So if our Y is equal to 0 right there, we can go back up to our equation 6.9 right there. And if we plug a 0 in here, 0 divided by C right there, this is still going to be 0. So 1, this whole term goes to 0 right there. So 1 minus 0 is simply 1. So if we multiply 1 by 3/2 V over A, that leaves us with just 3/2 V over A. So that's how we get our tau max relationship shown here in equation 6.10. So now we're going to continue on looking at this shearing stress right here, our tau xy, and some other types of beams right there. So another common type of beam right here is our American Standard S beam, and also our wide flange W beams right there. So this relates to equations 6.6 and 6.11 in our textbook right here. And we relate back by looking at these beams by going over here to this figure right here. We have A, B, and C right here. So let's take a look at A first. So with A right here, what we have, this is a wide flange beam right here, and in part A, this is the area for finding the first moment in the flange area right there. So this is our flange area right here that we're looking at right there. So this is defined as A, B, D, E, F, and G right there, whereas the bottom flange is the same A through G, but prime right there, A prime through G prime right there for the bottom flange right there. So now what we can see there's our centroid right there. Move to C, so there's a neutral axis right there from C to C prime right there. So, and then we also have now here, if we want to find the moment of inertia in the flange, we can take this section right here at A to A prime right there through that top flange. Now we can do the same thing here in part B, where we're trying to now find our first moment in the area of the web. Well, what is the area of the web right here? So our area of the web is defined from E, F, E prime, F prime right there. So this rectangle right there is going to be the web for this wide flange beam right there. So now we can see the thickness of this web right here is defined by this variable t right there for the thickness of the web right there. We see from our neutral axis up to where we're looking at our section right here, our B to B prime right there, when we're trying to find it again in the area of the web for this first moment right there, we're going to go the section from B to B prime right there. That distance between our neutral axis and that line there is going to be given by y. So coming back to our governing equations over here, 6.6, we can see that average, our tau average right here, is equal to our VQ over IT right there. Again, now we've defined that T right there by the thickness, so we'll clear this all off for a second. And we can see now that that thickness right there, there's our T right there, the thickness of our web right there, so that's where our T value comes in there. So our shear force times Q over I times that thickness right there. We also now have our max value right here. Well, this is going to be defined when we have our V all over the A of the web right there. So the A of the web right there, we can find that relationship right there. If we know the height of that there in between those two, and we know the thickness right there, we can get the area of the web right there. And this goes back to our equation 6.11 in our textbook. So as we continue on with our discussion of stresses right here, now let's take a look at the distribution of stresses in the narrow rectangular beam. So we're still going to go with that simplistic beam right there of the narrow rectangular beam right there. And what we want to do is now consider this cantilever narrow rectangular beam where we have it subjected to a load P at its free end. So this is what we have over here, and this figure right here, as we can see, there's our cantilever beam right there, there's our fixed end, here's our free end, and here's that external load P applied at our free end right there. So what we can see from that is our shear stress, our tau xy, is given by the relationship shown in equation 6.12 in our textbook right here, where tau xy is equal to 3/2 times our P over A times 1 minus y squared over c squared right there. And our normal stress, our sigma x right here, is equal to a positive P xy all over I. And this equates back to equation 6.13 in our textbook. Now with this, our shearing force V is constant, and it's going to be equal in magnitude to our load P right there. It's applied at our free end right there. Another thing to note with this here is that our normal strains and normal stresses are unaffected by our shearing stresses. Now, if we go back to our St. Bernard's principle right here, the effects for load application mode are going to be negligible except in the immediate vicinity of the load application point. So depending on where those are, right at those load application points, everywhere except those is going to be negligible. Now if we come down here and we're taking a look at a distributed load across the cantilever beam like this right here, deformation of the cantilever beam could be shown as we see here in our diagram right there. And the thing to note is that the stress and strain deviations for the distributed loads are going to be negligible for typical beam sections of interest. So let's apply some of the key theory and equations that we saw earlier in this module to an example problem. So let's take a look at example problem 6.2 from our textbook. In this problem here, we have a timber beam AB. They tell us it has a span of 10 feet and a nominal width of 4 inches and an actual width of 3.5 inches. Now this beam supports 3 concentrated loads as shown below in our diagram here. So we can see we have a 2.5 kips load, we have a 1 kip load and 2.5 kips right here, the third load right there. Now knowing that for the grade of timber used, our stress right here, our normal stress, allowable stress is equal to 1800 psi, and our allowable shear stress right here is 120 psi. They give us that information for this grade of timber. They ask us now to determine the required depth D of the beam. Now, a thing I want to mention right here as we take a break, I'm going to erase this right here. And for this problem here, this is a pretty simplistic problem, and they give us a lot of information in this problem here. Now, as we proceed forward with some of the other design problems there, they might not tell us the grade of timber exactly what our stresses are for this. This may be something that we need to look up. They might say, choose a grade of timber, and then we have to specify one and double check everything. Or they might tell us the grade of timber, and we need to know where to go to get the information that we need to plug into this right here. So this is a little bit more simplistic problem right here that they gave us with all that information right in the problem statement. So just want to let you know where we're headed with these types of problems in the future is that not everything is going to be nice and neat and given to you in the problem statement necessarily. But for this case here, we're just going to practice our governing equations and apply our theory that we learned right here. This is a great way to do that. So continuing on to this problem, they asked us to find the minimum required depth D of the beam right there. So this right here is this criteria here. So this again is another interesting design type of problem. They've already specified all the materials for whatever it is. Our client, whoever it is, has already told us this is exactly what it's going to be. These are our properties. But based upon that, we need to then calculate what dimensions we can use. Now this could be given in a different way. We had set dimensions we had to use, and then we had to figure out which material to use and look up those properties there. Or it might be something where both of those was freedom of design criteria right there, and you had to specify the dimensions and the type of material to meet certain specifications. So again, just a little bit of hint into where this is going. So back to this problem again here, we can also see here the total span of this is 10 feet right here. Then it's 2 feet from the end to the first applied load, another 3 feet to the next load, another 3 feet to the next load, and that's 2 feet away from our end over here at B. So as we're reading through that problem statement, looking at our initial diagram right there, we should be coming up with our mind a kind of a procedure for analysis or a strategy on how we're going to solve this problem right here. So how we're going to solve this right here, first thing we're going to need is we're going to need a free body diagram. So with this free body diagram, we're also going to have a shear and bending moment diagrams, and these are going to be used to determine our maximum shear and bending moments. Now, the resulting design that we're coming up with here must satisfy both allowable stresses right there. So it gives us our shear stress, our allowable shear stress, and our allowable normal stress. So those are our criteria that we have to meet. So we need to design something that meets those criteria. Now we can start with some assumptions. So again, this goes to our setup page and what assumptions are we going to make right here. So we can start by assuming for one assumption that one allowable stress criteria governs and solve for the required depth. So we're just going to go off of one of the allowable stress criteria and use that to solve for that depth D. Then what we can do is once we have that depth D, we can go back and use that depth right there with the criterion to determine if it also satisfies the second stress criteria right there. Now, if it is the case where the stress is greater than the allowable stress, we need to revise the design using this, the second criterion. So we can go back, solve it the other way, or we might just change the depth a little bit. And this is something right there where it quickly goes from something we're doing with the analytical hand solution right here, and maybe we want to try a bunch of different diameters. We want to program this whole algorithm in to something like MATLAB or even Excel or possibly Python right there, and plug these in and run through a bunch of different dimensions right there, in this case just the depth right here, and take a look at what it spits out. If we have, okay, this is we're going to cycle through these values right here for the one criterion for our stress right there, and we're going to cycle through the values for our D right there, and does it meet the criteria over here for our other allowable stress right there? If it doesn't, how can we change? We keep iterating that D and running it through a loop right there until they both do meet those criteria. So just something to think about as we move forward. We're not doing it by hand solution. If we have, fifth, sixth, seventh iteration, we're still not getting it, maybe we do quickly need to see, switch to a numerical solver for those types of problems. And again, this is one here where we didn't have to specify the material. They gave us the material that we're using with those criteria. Maybe there's a problem here where we want both the dimensions we need to come up with in our design process, and we need to also come up with the material types to meet the stress or strain or whatever it is in a different problem that they ask us to meet for our specifications from the client. So that case right there, we might have to have multiple arrays or even matrices of these values right there that we then program in. So this again, just taking it past this simple problem that we're working now, thinking ahead of the types of problems we might be dealing with in future courses. So with all that information, back to our simple problem here, we can take a look here, and what we want to do is we redraw out that initial diagram right there. We take the information from our problem statement right there, and we say, okay, this is a timber beam, AB, has a span of 10 feet. There's our 10 feet right there, and it supports 3 concentrated loads, so 1, 2, and 3 right there, and we know the location of those loads from our initial diagram right there. And if we know, and they give us the grade of that timber, and we now have here that our max allowable normal stress is 1800 psi, and our maximum allowable shear stress is 120 psi right there. From that, this is what we need to find. Here's our find section if we were doing this out by hand for our setup page right there, to determine the minimum required depth D, which is this depth right here of the beam. So now we can go through a little bit more organized plan of attack right here. So we see our solution right here. First thing we're going to do is develop a shear and bending moment diagrams from our free body diagram as well, and identify the maximums. From there, we design the beam based on the allowable normal stress. We're going to use the normal stress first to solve for that depth right there, and we'll check that against our shearing stress right there. And we may have to go back into the design process and redesign the beam based on the allowable shearing stress if this is needed and it doesn't meet it when we do that check with the shearing stress right there. So it is going to be an iterative process, which is great to learn now because that is true as we move forward to future courses where we're actually doing some more of this design work on our own and have a little bit more freedom with that it is an iterative process, and we need to keep going back through and double checking things if these tests, these double checks, don't work out in our favor. So as we begin our solution, the first step was to draw out our free body diagram, and from our free body diagram, develop our shear and bending moment diagrams. And from that, we're going to identify our maximum. So the first step in this procedure right here is to draw out our free body diagram. So that's exactly what we do here. Now the thing that we know is from these 3 concentrated loads, if we add those all up together, 2.5 plus 2.5 plus 1 kip right there, that's a total of 6 kip. So now we know for the simply supported beam over here like this, we can divide that and we have a force right here, reaction force right at each end of this is simply supported, that's equal to each other and equal to, in sum, to the top right here. So if this is 6, this is going to be 3 and 3. So 3 at A and 3 at B right there. And we now know the difference between all of these there. So the next thing we want to do is figure out our shear at each of these. So if we start here at A, our shear, going from right here to right here, we can look, well, right from our free body diagram, so drawing it directly underneath there. There's our shear right there, 3 kips. So it goes right all the way up here now, a positive 3 kips all the way up here, and then we hit this 2.5, we go down. So 3 minus 2.5 brings us down to half a kip right there. So right there, there's our half kip right there. So now we have this one half kip right there that goes all the way up this distance of 3 feet until we go down another 1 kip right there, which brings us down right here. So if we have half kip, we go down 1. Now we're down here at negative 0.5 kip. So 0.5 minus 1 is negative 0.5, so we stay at negative 0.5 all the way across this for another 3 feet right there until we get to E, which goes down another 2.5 kip. So 2.5 and a negative 1, or negative 2.5 and negative half right here gives us a negative 3. Stays at negative 3 till we get back there, and then we have this 3 kips that goes back up and brings us back to 0. So that's how we're drawing out our shear diagram right here, right from our free body diagram. So we can see how important it is to draw it right directly beneath that free body diagram and to have an accurate free body diagram from that right there. So now what we can do for our moment right there is we can take a look at this and say, okay, well, what's going on at each of these points here? Well, we can take the area under our shear curve to get our moment values right there. So what we can say now here as well, if we go from here to here, this is going to be 3 right there, and this right here is going to be 2 right there. So therefore, this right here is going to be an area within this right here of 6. Yeah, so it's like the 3 and the 2 feet across and our 3 kips up right there is going to give us a value of 6 kip feet right there. So then we go down to the next one right here in this next stage right here, and we can say, okay, well, at this one right here, we're now going from a moment right there at 6 kip feet right there all the way. Now this is an area right here of 1.5 because this is 3 times 0.5. So then we go up here, and that brings us up to 7.5 kip feet right there. Then we drop back down. The area right here is 3 times a 0.5 right there. So it's a negative 1.5 right there. Sorry, negative 1.5 times 3 is negative 1.5 right there. So that brings us back down to 6 kip feet right there. And then this is a negative 6 right there that brings us right back down to 0. So we start at 0. We go up to that value of the area of our shear diagram right there to 6 kip feet. Then we add in the area right there to this right here, brings up to 7.5 kip feet. We subtract this because we're on negative of 1.5 kip feet, which brings us down to 6 kip feet. And then we subtract this area of this one here, which is negative 6, brings us back down to 0. So now that's how we can easily draw our shear and moment diagrams directly from our free body diagram. So we can look at these diagrams right there, and right from there we can see, well, our max shear right here is a 3 kips right there, and our max moment right there is at 7 kip feet right there. So that's our 7 kip feet right there. Right from the diagrams, we can get the max of both of those. So we now have the maximum shear and bending moments that we acquired from our shear and bending moment diagrams on the previous slide. So what we can do from here now is go back to our procedure for analysis right here. What we want to do is realize that the resulting design must satisfy both the allowable stresses. And what we decided to do with our procedure for analysis was we were going to start by assuming that only one allowable stress criterion governs and solve for the required depth D based upon that criterion from that one there. So we had also decided that we're going to start with our allowable normal stress right here. So with our allowable normal stress, we have this relationship that we've seen before, that our allowable normal stress right here, our sigma ALL, is equal to our maximum moment divided by our S right there. So from that right there, we can plug in these known values. So our allowable stress was given to us in this case here as 1800 PSI. So we have that value right there. So this is our allowable stress right there, allowable normal stress right there. So this is equal to our maximum moment. So now we can go back to our previous slide there, and from our graph, we can take a look at that, and we convert this, again, pay attention now, rather than feet, we convert it to inches here, and we have that conversion in our previous slide there. So now this is 90 times 10 to the third pound inches right there. And the reason we want to do that right there is because we also have our denominator here, our value here for S right here in inches right there. So we can look at this right here. So this is our value for S right there. So we have this as 0.5833 inches times our D squared right there. And this is coming from this relationship up here. So we can plug this in now, and we find out when we solve for D, D is equal to 9.26 inches. So now going back to this governing equation right here for our allowable normal stress, we do see this S down here, and we can see this value. The question is, where did this come from? So we come down here to our side note over here, and we see we have this relationship that we've seen this before. The S is equal to our I over our C value right there, which in our case here for this shape beam that we have up top right there, we can plug in where our I is equal to our 1/12 BD to the third right there. So we plug that in, divide by our C, and we have a relationship right here between our C and our D, where our C is equal to our D over 2. So for our value for C here, we can put in that D over 2. And what this reduces to when we plug in our value for I and our value for C here, relating it back to that D value right there, which this is our D value right there, we can plug this in, and we have 1/6 BD squared right there. Well, we have values for all those right there for our B. So our B is equal to 3.5 inches right here. So we can plug that in for our B value right there. And we see that S is now equal to 1/6 times the B value, which is 3.5 inches right there, times our D squared right there. So now we can do out our math, and we find out 1/6 times our 3.5 right there. We end up with that as our 0.5833 times D squared. So that's where this denominator came from when we're going up here to the sigma allowable right there, as we plug this relationship in for our S on the bottom of that relationship there, leaving us with one equation and one unknown at this point right here. We just had our D value right there, so we solve for that D, and that's where we get this D is equal to our 9.26. And again, double check your units. This is in inches. So now that we've solved that based on just our normal allowable stress right there, we need to double check that against our shearing stress right here. So we go back to this governing equation that we solved for earlier within this module here, that our allowable shear is equal to 3/2 times our V max right there, which we can get off of our diagrams right there, divided by our area. So we plug this in, 3/2 is 3/2. Then we found this right here, our V max right there was 3,000 pounds right there, all divided by our area, where our area is 3.5 times our 9.26 inches right there, which gives us a value of 138.8 psi. Now, since the allowable, according to our problem statement here, our given specifications right here, our shear allowable is equal to 120 psi, then our depth right here of 9.26 inches, this is not acceptable because this 138.8 is greater than this 120 psi. So we have to redesign the beam on the basis of the requirement now that our shear is less than or equal to 120 psi. So that's where we can go backwards now, and rather than starting with our normal allowable stress, we start with our shear allowable stress right here. Redo that, so our equation right here, our T sub m is equal to 120 psi is equal to our tau allowable, our allowable shear stress right there. So this right here is 3/2 times, now we have our V max right there, which we have a value of 3,000 pounds right there. And we have our area here, where the one thing in our area we don't have now is this D, so we can back out our D based upon that 120 that they gave us. So in this case here, our D is 10.71 inches, which we could then plug that back up into our equation above here and double check that it is less than the 1,800 psi. Double check that, and it does check out right there. So that's how we did it. We went the wrong assumption first and compared against our normal allowable stress, and we found out no, that's not acceptable. So we had to go back down here and do it from our shear allowable stress right there.